I have the pleasure to welcome you today to the second already EMD International Site event. Today we are meeting with Lasse Svenningsen, Research and Development Manager at EMD, who's going to talk about the lifetime assessment using windPRO, site compliance and load response. Lasse, over to you.
Thank you, Alexandra. Good afternoon, everyone, and welcome to this presentation. So what I'm going to talk about today is the recent IEC 61400-1 Edition 4 standard and lifetime assessments, both using windPRO site compliance and load response. As Alexandra said, my name is Lasse Svenningsen, and I'm from EMD International in Denmark. And so the agenda that I'm going to take you through today is first a bit of PowerPoint. We will look into site assessment, in particular the -1 Edition 4 standard, which are the news and how does it relate to load assessment. And then I'm going to shift to a lifetime analysis, look at the different standards, and in particular zoom in on the DNV GL standard and the possible calculation approaches in that standard. Then we're going to make a shift, hopefully without any issues, to a brief windPRO demo of how to do the assessments in site compliance and load response. And in the end, there'll be time for some questions. I don't expect this to take more than around perhaps 45 minutes in total. So please ask your questions in the SpotMe app during the presentation. And I'll get to them in the end. So first, let's zoom into site assessment. So the basis of all this is the -1 standard, and this standard defines the design requirements for wind turbines. And it also defines the standard classes which are used for wind turbine design. So these classes are the familiar, for instance, 1A or 3C, or the class S, the custom classes. So the classes are characterized by the design parameters, the IREF and VREF. And I think a lot of you have seen this table 1, which defines these classes and design parameters. So if you read on the standard, you'll get to section 11, which is where the guidelines for site assessments appear. And this is basically the guidelines for how to determine whether a particular turbine class is suitable for a given set of site conditions. So it defines a number of checks for the site and wind climate parameters and also the limits that they need to be within. And if you read a bit further on in the standard, you'll also read that if some of these checks fails, you need to do a load calculation, which is then defined in the following sections. So this is the front page of the standard. It was released in February last year, long awaited. So fundamentally, it is in many regards closely aligned to the contents of the Edition 3 standard. However, there are some important adjustments, in particular for site assessment, and I'm going to take you through those. So one thing is that, which is of course a general thing, is that there are several new design classes. So one thing is that a new very high turbulence class has been introduced. It has a reference turbulence of 0.18. And then a sort of tropical typhoon classes have been introduced. That's basically an option which can be added to all the existing classes, which will increase the extreme wind speed limit, the VREF, to 57 meters per second. So these classes are basically here in the table. Okay, so but for the actual site assessment, there are some changes, and let's first. So the terrain complexity check, which is relating to the terrain around the wind turbine locations. So it has completely changed in the Edition 4 standard, but the purpose is the same. It is to, of course, to identify the degree of terrain complexity, and in the end to quantify whether this turbulence structure correction need to be applied to the turbulence. This is what we call the CCT. So the purpose is the same, but the calculation procedures have been changed completely. And then in the new standard here, there's an explicit split in the wind climate checks into fatigue-related checks and ultimate checks, which relate to the extreme conditions. And there are some important changes in some of these checks, and I'll take you through those. So the main, the one with the main changes I've listed below here. And first, the wind distribution. An additional check has been introduced on the viable shape factor, what we call the K factor. And sort of the illustration here on the right is just an illustration of the general wind distribution check, which I've borrowed from a close partner of ours, Morten Nielsen. He's done some really nice illustrations, and I'll use them in the for the other checks as well. So the wind shear has been changed to an energy-weighted sector mean, and the same is the case for the flow inclination. For air density, so it's fundamentally the same. However, if the air density exceeds the design limit of 1.225, the edition 4 standard allows a correction if the mean wind speed is less than the design mean wind speed, to give some margin there. So for the ultimate checks, 3 new checks have been introduced, which relate to the turbulence. So one for checking the ambient 90% turbulence, one for the maximum center wake turbulence. So that's simply the worst combination of 90% quantile of turbulence and wake added turbulence. And then the extreme ambient turbulence, which is the joint 50-year event of wind speed and turbulence. And then extreme wind, it was there before. However, 2 new corrections have been introduced. One to correct the safety level, because apparently it has been identified that there was not enough safety for particular types of extreme wind distributions, Gumbel distributions. And so to correct for this, a safety correction might need to be applied. And then the standard also explicitly defines an air density correction. So those were the main changes in the edition 4 standard relative to edition 3. So if you want to do that in windPRO, site compliance is the tool. So we've implemented all the checks in edition 4 relating to site assessment. We already had edition 2 and 3, and our implementation has been certified by TÜV Süd for compliance with the standard. And I'm going to give you a brief teaser of how easy it is to do this calculation after this PowerPoint. So, but what happens if some of these wind climate checks fail? Well, a load assessment is required, and the load assessment is divided into a number of design load cases. There's a long list, which you can see on the right of the slide. So if the fatigue checks fail, these 4 design load cases are required. They relate to fatigue. So that's the DLC 1.2, which is normal operation, power production, and then we have 3.1, 4.1, and 6.4, which are startup, shutdown, and parked. And they are all implemented in our load response module in windPRO. So if the ultimate checks fail, it's more complex, and I line up here the design load cases which needs to be checked, and also sort of what they include. And generally, so this is quite specific to the particular turbine design, and it's generally advised to consult the manufacturer if there are significant incidences in these checks. So how do we actually, if we have calculated these design load cases for fatigue, how are they actually assessed? Well, we use something which is called fatigue damage equivalent load, or DEL. And we calculate these damage equivalent loads for the site conditions for each turbine and component, and compare them to the DEL for the turbine. So the DEL design here represents the strength of the turbine. We can also take the ratio. We call that the load index, and obviously this ratio need to be equal to or less than 1 for the loads to be okay. So it turns out that this load index is closely related to the lifetime estimate. So I'll get back to that later. But it's a perfect opportunity to shift to the next topic, which is lifetime analysis. And so one important thing here is that the primary standard for lifetime analysis is still the design standard, the -1 standard, because it defines how to characterize a site's wind climate and how to do the load calculations. And site assessment is actually just a special case of lifetime analysis, namely that we are testing whether the estimated lifetime of the turbine components on the site are equal to or higher than the design lifetime. And of course, this also defines the potential for lifetime extension, namely the difference between the estimated site lifetime and the design lifetime. So there are several standards which focus directly on the task of lifetime extension analysis, and we have the DNV-GL standard, we have the UL standard, and the IEC-28 standard, which is still under production. I think last I checked, it was supposed to be released next year. So in this, I'll focus on the DNV-GL standard. I think it's a very good standard. So if you haven't read it, you should be able to find it on the web. It's quite short, focused on concise, and includes what needs to be included. So the DNV-GL standard splits the lifetime assessment in 2 parts, an analytical part and a practical part. So the analytical part is calculations, and the practical part is the inspections. Of course, a very important part of our lifetime extension. So I'll focus on the analytical part because that's what we can handle in a software. And the DNV-GL standard describes 3 analytical approaches, 2 deterministic and 1 probabilistic. So the simplified approach uses a generic turbine model, and that is to be used if the original design of the turbine is not available. Then you need to resort to a generic approach. You also need to quantify the uncertainty of using the generic model. It's not used in any calculations. It's just a part of the documentation. So the detail approach is also deterministic. That's what you use if you have the specific turbine design available. And because it's deterministic, no uncertainties are considered here. So the probabilistic is the approach where all uncertainties are accounted for, all relevant ones at least, and you do a full structural reliability analysis, and that is checking if the probability of failure in each year of operation is less than or equal to 0.5%. So my colleague René Slot presented some results using this approach, which we have implemented in-house at EMD in a very efficient setup yesterday. So you can find the recording in the program. So what I'm going to focus on is the 2 deterministic approaches, the simplified and the detailed one. So one thing I first need to emphasize is that when I say lifetime, I mean fatigue life. And so the things like extreme events are not reassessed according to the DNV-GL standard, and wear, corrosion, abrasion are all part of the practical assessment of the wind turbine. So they're not accounted for. So lifetime in this context is fatigue life. So the way that we do load calculations in the windPRO software is that we use load response, which has a response model. So it's nothing but a very smart pattern of pre-calculated damage equivalent loads, which can be used in a very fast and accurate regression to calculate damage equivalent loads for any site climate. And that approach allows to use either a generic model, that's the simplified approach, or a specific model in the detailed approach according to the DNV-GL standard. So we talked about the load index a bit earlier, and here's the expression which links the estimated site lifetime to the load index for a particular component on the wind turbine. So the So it's basically the load index to the power of minus m multiplied to the design lifetime. And m is then the Euler exponent, which is a material parameter characterizing, could be 14 for carbon. So the interesting part here is the numerator, what we call the normalization load or the design load. Because for the simplified approach, the generic approach, we don't have this. So we have to calculate it as the loads for the design climate, which means that we cannot account for any design margins in the turbine, that the turbine is actually a bit stronger in certain components than was required in the standard. So for this simplified, sort of detailed approach where you have the specific information, DEL design is actually the design or certification loads from the manufacturer, including these margins. So generally, we would expect the generic approach to be slightly conservative. So a nice thing about this equation is that it is a ratio of damage equivalent loads, and it turns out that errors from using a generic model tends to cancel out in this ratio. And this is the reason for the generic approach actually being surprisingly accurate in many cases. So if you want to do lifetime analysis in windPRO, you can use our current versions. It's 3.3, 3.4 is coming out these days. And of course, you'll use load response, as I mentioned earlier on. The generic models are included. They're split into different rotor sizes, so less than 90 meters, larger than 90 meters, and larger than 160 meters. If you want to use a specific model in the detail approach, you would need to get a load response file from a manufacturer. They can implement that in-house using their own internal simulation tools, and they can share in a very secure way with the loads being pre-normalized and the file being encrypted and license protected. So if you are a manufacturer and you're interested in doing this, you can contact me and you can get the specification for how to implement your own load response files. So in the coming version, we will be increasing the emphasis on lifetime according to the DNV-GL standard and aligning even more to that standard. And for instance, including this uncertainty on the generic model. I also have to mention that we have this in-house tool at EMD, which can be used for a very efficient full probabilistic reliability approach, which my colleague presented. And if you are interested in that, you can contact me or my colleague René. You see the emails there, and we can have a talk about that. So just a slide here to summarize before I shift to the presentation. If you want to site assessment, we have implemented edition 4 of the -1 standard for you. We also have edition 2 and 3. It's in site compliance. And there are some quite important changes in edition 4 compared to edition 3. And our software has been certified by ChifSuit. If you want to do lifetime analysis, you can do the simplified and detailed approaches according to the DNV-GL standard using windPRO load response. The simplified just requires the generic models, which comes with the module. For the detailed approach, you need to get a load response file from an OEM. And as you see, you can do lifetime assessments using load response, but we will make it even more visible in the coming version. Good. So I'll shift to windPRO now, and hopefully that works without a problem. So I'll, oops, drag it in here. And so you see here I have a layout of 45 turbines. It's in southern Brazil. From the map, you can probably see that there is some kind of large terrain escarpment here. I have prepared 2 calculations here, one in edition 4, and I'll open that. So I could set it up and show the calculations. It'll not take very long, but I want to save the time so that you can ask questions and get on with your day. So if you're not familiar with site compliance, so the first tab here basically sets up the fundamentals of the calculation. So what kind of data do we have? Which flow models? Do we want to include a load calculation and curtailment? And then you define the design standard. See, we have 3. And then you define the design class. Since this is edition 4, you can check the tropical option here to get the typhoon classes, and you can select the different design classes, which you saw in my presentation. So in this case, we will assess this class 3A, and I'll just step briefly through the setup tabs here and go to the IEC checks. So I have 2 masts here, and I have the 45 VTGs. Have a link between each mast and VTG, so I know which data to use for which VTG. Possibility for long-term correction, I haven't used that here. I have a WASP calculation, and then I have my IEC checks. And this is the setup according to the edition 4, and you can see the fatigue conditions and the ultimate conditions and the terrain complexity here. You see we have a traffic light here, so this indicates the worst affected turbine in the layout, and you can actually see this link that I also presented in the presentation. If a particular check fails, there's a link to the design load cases required, and we indicate that here. You can see for the fatigue ones, it says that these checks are implemented in load response. There's also some exceedances here for the ultimate condition. So I'll just briefly take you through the checks that I mentioned in the presentation, where there are some changes relative to edition 3 of the standard. This is terrain complexity. So basically, for each turbine, each of the 45 turbines, it gives us a complexity category, which can be high, medium, low, or no terrain complexity. You can also go to the results table, where we can expand the results for each turbine. For instance, this one, which is in the low complexity category, we can see the parts that has been calculated. So it's a number of terrains which have or planes which have been fitted, and there are some parameters which have been assessed according to the standard, a terrain slope index and a terrain variation index. And it appears here that it's the terrain variation index for some of the fits here at the larger radii, which are exceeded. You can also go to the graphics and you can visualize the fits. Of course, it's always a bit difficult to visualize something which is 3-dimensional in 2 dimensions. Good, and maybe I didn't mention here, but you can also see the turbulence structure correction. So this is this factor which is multiplied to the turbulence. So the wind distribution, that also has had some changes. So this is the check here. You see the site and the design or the turbine and the design distributions, and there are some minor exceedances here within the check interval. The new check here is this check on the K factor. So here we see the K factors on the y-axis, and then the ratio between the mean wind speed for the turbine divided by the mean wind speed for the design class. And then the IEC standard requires the values to be within this blue box here. See, some are outside in this case. So that was the wind distribution. The effective turbulence is not changed. The flow inclination. And this is where we have the new estimate is the ND weighted average. So you have the ND weights here and the sector-wise flow inclination. You can see the ND weighted average here. Wind shear is the same. Again, you can see the energy weights and the energy weighted shear. We have quite large shears on this site. Particular for we have one turbine here which has a shear above 0.3. And finally, air density. In this case, it's Brazil. so it's quite hot. So the air density is low, so there's it does not exceed the design limit, and so this new correction is not applicable. And then we have the ultimate checks. We have the 3 turbulence checks here, which are quite similar. I think I'll not go into detail with those, but I'll jump to the extreme wind. So this is a Gumbel fit, which represents the extreme wind distribution. And we can go to the table here, and we can see this is the raw estimate, and then we can see the correction factors here. Here we have the air density correction, and for this side, this new safety correction factor does not apply, so it's equal to 1. And you can see the corrected estimate here, and it's all within the limits. I think with this, I'll click OK, and then I think demonstrating the lifetime extension is not really useful or meaningful for a standard which is just released last year. I don't think any edition 4 standards turbines need to be lifetime extended. So I have a presentation here or a calculation for the edition 3. And so it's the same setup. I've just selected edition 3, and it's again a 3A turbine. So what we do now is that we click that we want to include load response. So what happens here is that a tab appears. So load response is integrated inside site compliance, and it makes a lot of sense because it uses the results of the IEC checks for the load calculation. The checks in edition 3 here, the results are resemble quite a bit the checks in edition 4. You see the results are slightly different, you might remember the results from the previous calculation. If we go to load response, so it's the setup is quite simple. You select the response model to use, and in this case, I have a turbine with an 80-meter rotor, so I select the smaller one here with the rotor diameter is less than 90 meters, and I open the check here for fatigue load calculations. And you can see the setup that I have the relevant design load cases. They have been activated here, and I basically click calculate. So it's very easy. And now it's doing full load simulations here for 45 wind turbines. It takes a few seconds. Excuse me. And we have the result. So we are interested in the lifetime estimate or the fatigue life estimate. So we go to result table here, where we have the results for all the 45 wind turbines. And what it shows here in the collapsed view is the lifetime for the worst affected component, so the component with the lowest lifetimes. And so we see here that we have lifetime estimates down to 22.3 years. We can expand that to see the estimates for different component and sensors. Okay. So it's a bit hidden here, but it's as you see, it's actually very straightforward to do the calculation. So if we now wanted to do this calculation for a specific turbine modeling following the detailed approach of the DNV GL standard, I would need a load response file from a manufacturer. So I would need to go to when I once received I received the file. I would need to go to the windPRO data load response folder and put my file here. So in this case, I have a specific file here. It's from the famous turbine manufacturer EMD. So it's a specific 3A model here. So I put that in the folder, and if we look in the list, we can see that it actually appears here. And so I can go in and then I can recalculate my results. I think before doing that, I'll just show you here the normalization loads. You see for a specific model, we have the design loads included in the file. So that's the default setup. I could choose to do it in the same way as I did for the generic model, where it's always fixed to calculating the design loads. But I want to include the margins here and use the actual design loads I get with the file. I press calculate, and we do the load calculations for the specific model, and we get the results. And we can go in and check. Again, we see actually that the fatigue lifetimes in this case are a bit higher. So we see that in this case, the margin has actually meant a small difference here in terms of a couple of years or so for some of the components. So this is how easy it is to do site assessments and lifetime assessments in windPRO site compliance and load response. And with this, I'll see if I can get back to my PowerPoint. And we have time for some questions. So while I look at the questions, you can see on this on the slide here, if you want to know more, you can go to EMD's homepage. You can see information about site compliance and load response. You can contact our sales or support if you have technical or sales-related questions. Or if you want to implement in-house models for load response, you can contact me. So I see one question here. So there's a question which reads, has the load response module been verified and validated against real-life cases? Yes, so the way that it's been validated is obviously that it's been, since it uses a response model, that part has been validated and actually certified by CHIP for the accuracy compared to doing the load simulations directly, which is very time consuming. But we have also verified the generic turbine models against specific models, and we saw a very good agreement. Of course, these specific models are commercially sensitive, so we have not been able to present this. But so in general, yes, there has been a quite extensive validation. We've actually had both an industrial postdoc and following that an industrial PhD working on these matters. Yeah, let's see, any more questions? So there's a question here. It's someone who would like to use SCADA data for the lifetime analysis. And as it is right now, it is not possible. However, and I'll now take a bit, see, back here. And so this DEL site, so the damage equivalent loads for the site, we could estimate that based on SCADA data. It is quite difficult, but it is possible. It is not possible in windPRO right now. It is of course something that we hope to be able to provide in the future. So very good question. Oops. And there's a question here whether it's possible to design curtailments with the tool. And yes, it is possible to take into account curtailments in the load calculation. It does not do an optimization for you right now. So if you have a curtailment scheme, you can implement it in your wind turbine objects, and it can be included in the calculation. You just need to check the box curtailments, which is next to checkbox for load response. Let's see, is there any more questions? So there's a question here whether we would consider to develop the load model further to so it would be possible to customize component sizes, material thickness. Yeah, that's a very good question. So we want to make the tools more accurate. We have done quite a few analyses which shows that for a generic approach, that's also what I indicated in the presentation. Small differences, or even quite large differences in some of the dimensions, don't influence the results a lot because of this load ratio, where a lot of the errors cancel out. So for the generic model to be accurate, it does not need to be accurate in an absolute sense. We just need to have the right sensitivities to an increase in turbulence. And it turns out that that the design does not need to be spot on to actually provide very accurate results. But of course, we won't stop the development here, so we will try to improve it in the direction that you indicate. So there's a question whether most manufacturers provide a load response file, and it's a question which I cannot answer. I know that we have provided the specifications to many manufacturers, but often the sharing of the files would be directly between the project developer and the manufacturer. So we would not be a part of that. But of course, you can always as part of your tender or as part of your general agreements with the manufacturer, require them to provide you the load response files, and they can contact us for the specifications of how to implement it. There are a few more questions here. Yeah, so there's a question whether this could be run in a batch mode for a large number of projects. And as it is right now, it is not possible with windPRO. We are working on opening up windPRO with scripting interfaces, and that would make this possible. So we are awaiting that. In-house at EMD, we have this also set up to do batch calculations, an identical setup, so we can do that. So if it is for a particular project or anything like that, you can reach out to me, and we could find a solution for that, I'm sure. Yeah, so there's a question here whether the shear calculation inside compliance, which is energy weighted, if that's the way according to the standard, or if it's the frequency weighted. So as I understand the question here, so in edition 3, the text in the standard is not fully or very clear about it, but in edition 3, the general interpretation was that it was the frequency weighted average, whereas in edition 4 here, it is explicit that it's the energy weighted average. So there's a question here whether the dynamic model of wind turbine considered in the load calculation. I'm not sure exactly what is meant. Perhaps it is the dynamic wake meandering model, which is also a part of the edition 4 standard in an appendix. I didn't mention that. It is something that we have on our list. We would like to implement it. It is a quite big leap from the current setup in the standard using effective turbulence. So we are looking into ways of finding an elegant way of implementing and making it available to our end users. So it is definitely something that we are working on. Yeah, there's a question here whether we would want to implement a 15 megawatt turbine. It's also sort of one of the standard generic turbine models out there. I think we have heard about it. So if you are welcome to send us a reference to where the turbine specifications are available, and we can definitely put it into the software. That's no problem. And I think then there's a lot of questions coming in here. It says if a component is replaced, whether we are able to recalculate that. No, and as you see right now, you could say our lifetime calculations are quite hidden, so it's something that we will be building upon, and I think this is definitely an important scenario, that you have components being changed in particular during the extended lifetime, and this is something that we will look into how we could make that available in a user-friendly way. Then there's a question here: how much calculation time does it take in load response for a single project of 30 to 40 turbines? So I actually showed you that. So I did the load response calculation for 45 turbines, and it takes less than 10 seconds. Of course, it requires that the load simulations for the response model have been done up front. And then I think our last question here: how do you see it when the lifetime is offered by OEMs at wind farm level assessment instead of individual turbine positions? Does curtailment feature support this? Yeah. I'm a little bit in doubt what is meant by the lifetime defined on a wind farm level. I think the lifetime assessment always needs to be conducted on a single turbine and component level. So I wouldn't know how to come about it on a wind farm level, but maybe you can send me an email with some more details with this question, and we can I can come up with a better answer. And then the question here is, does the curtailment feature support this? Yes, and since the curtailment is implemented in the loads, it will automatically also be integrated in the lifetime estimates. So let's see. I think that was the last question. So with this, I will send the screen over to you, Alexander, and thank you everybody for your attention this afternoon.
I just want to invite you to join us tomorrow for the next presentation organized by EMD. This time we will have Morten Torgersen joining us, and he will present instant and accurate new geospatial dataset in windPRO. So I really hope to see you all there, and have a great evening. Thank you. Bye.